Hello and welcome to another video. Today we'll be looking at integration from Pure Maths Year 1, and let's begin with indefinite integration. As always, we'll start with a definition, an example, and then we'll go through the logic behind what we're doing. At the end of the video, I'll be looking into more detail about understanding integration to find area. But know that you're not required to find proofs of this right at this stage. So let's begin with indefinite integration. So when we integrate something, it's the reverse process of differentiation. Okay, so when we have dy by dx, okay, that's the gradient function, as say x to the power of p, well, if we want to get the equation of the line, we do y equals to x to the power of p plus 1 over the power plus 1 plus c. And we're going to see why we need to do a plus c when we do this example. So in this example, we have 3x squared plus 2x, and we need to integrate it. So first, we're going to do 3x squared. Okay, now we have to do p plus 1, so that's going to be 2 plus 1 over p plus 1, so that's going to be 2 plus 1, and then add, okay, 2x, that's going to be 2x. Now this is x to the power of 1, so we're going to have to do 1 plus 1 over 1 plus 1, okay, which gives us 3x to the power of 3 over 3 plus 2x to the power of 2 over 2, which then gives us x to the power of 3 plus x to the power of 2. Okay, now we need to understand why we're doing plus c. So normally when we differentiate something, such as if we had x squared, if we had, say, x cubed plus x squared plus 4, okay, if we were to differentiate this right now, well, we would get rid of the plus 4, right? But that means that when we then integrate 3x squared plus 2x, we have no way of knowing what the constant is. So that means instead of doing plus 4, we need to do x cubed plus x squared plus c. Okay, and this is indefinite integration summed up. Now we're going to look at definite integration, which is defined by two limits b and a. Okay, so we have our limits b and a, and we have the gradient function f dash x d of x, which means with respect to x. We then put it in square brackets like this, okay, and we put and so to get from f dash x to f of x, we integrate, okay, and then we do f of b minus f of a. I'm going to go through an example and highlight how exactly this all works. Okay, so we have the same equation as earlier, 3x squared plus 2x, and now we're going to integrate it. Okay, so first what we're going to do, we're going to put it in brackets like this, so we know that it's x cubed plus x squared plus c, and I'm also going to show why we don't need the constant c when we're doing this. So this is going to be x cubed plus x squared plus c. Okay, so that's our f of x, and then the b and a, that's 5 and 3, we put the upper limit here and the lower limit on the bottom. Right, now let's do f of b minus f of a. So we know that f of x equals to x cubed plus x squared plus c. So when we're doing f of b minus f of a, we substitute in b, so that's 5, so f of 5, which equals to 5 cubed plus 5 squared plus c, and then f of a is going to be this one here, so which is 3, so that's f of 3 equals to 3 cubed plus 3 squared plus c. Okay, now we're doing f of b minus f of a, so that's going to be 5 cubed plus 5 squared, so that's 125 plus 25, which is 150 plus c. Okay, and then we minus 3 cubed plus 3 squared, so we know that 3 cubed is 27 and that 3 squared is 9, so that means that it's 150 plus c minus 36 plus c. And we notice that the constants plus c, they cancel out because we're minusing them. Okay, so it's going to be plus c minus c. So what we're left with is 150 minus 36, which gives us an answer of 114. Okay, now we're going to use definite integration to find area. Okay, so let's start off. So we have a diagram here, and we have the equation of the line x cubed minus 8x squared plus 15x. Okay, so to start off nice and simple, we're first going to integrate from 0 to 3 to find the area from 0 to 3. Okay, so if we designate this as area A, and we designate the other one as being area B. Okay, so area A okay, let's just mark off this section, make sure nothing gets interrupted. Okay, so area A equals to 3, 0, and then we do x cubed minus 8x squared plus 15x. Okay, and that's dx. Okay, now so when we integrate this function, that's going to give us brackets, square brackets, x to the power of 4 over 4 minus 8x to the power of 3 over 3 minus 15x to the power of 3 over 2. Okay, and that's going to be 3, and that's going to be 0. Now we substitute it in, so we get 3 to the power of 4 over 4 plus, it's going to be minus 8 times by 3 to the power of 3 cubed over 3. Sorry, that should be a plus as well. There should be plus there. Plus 15. Yeah, that should be a 2 as well. It should be 8x, 15x squared. Okay, so that's 15 times by 3 squared over 2. Okay, and that's going to minus 0. Okay, because if we substitute 0 where x is, I think we can see that that'll just be 0. Okay, so that means that the area A would be 15.75 units squared. Okay, and we do units squared because they haven't given us any units to work with, so we just put it as units squared. Okay, so that's when you just have 0, 3, it's positive, and it's quite simple. Now we're going to move on to something a little different, and we're going to do the area from 0 to 5, which is essentially area A plus area B. Okay, so if we know that area A is 15.75, then we're not gonna, then all we have to do is add area B. But we have to be careful about when we do this, because when we integrate from 3 to 5, that's going to give us a negative value. And if we do a positive and plus a negative, if we just integrate the whole thing from 0 to 5, we're going to be integrating the positive and the negative. So we're just going to do 15.75 minus the area of B. And we don't want that. We want the area of A and the area of B. So when we're integrating this function from 0 to 5, we have to make sure that where it's we integrate it separately for where it's positive and where it's negative. So now we're going to do the area of B, okay, separately. So area B, so that's 5 and 3, that's x cubed minus 8x squared plus 15x dx. Okay, and we've already done this, so we can just skip to the next part, which would be 5 to the power of 4 over 4 minus 8 times by 5 to the power of 3 over 3 plus 15 times 5 squared over 2, okay, minus so, and we've already calculated what this is, okay? We already substituted in 3. Okay, so first we had to substitute 5 in, then we had to substitute 3 in and minus it. So we can just do this minus 15.75, okay? Which gives us a value of minus 16 over 3. And because area isn't negative, we can't, have the area as being negative, we times by minus 1, okay, which gives us a value of 16 over 3. Okay, then we do 16 over 3 plus the area of A, which is 15.75, to give us a value of 253 over 21, or approximately 21 units squared. Okay, so that's essentially all you're going to be required to know and do. There's obviously, as we go on through the course, we're going to learn more about integration. But for now, if you're happy with where we left off, you can end the video here. But now we're going to take a short detour, and we're going to learn why we're integrating to find area under a graph. And we're going to start with a graph of velocity, and we're going to start with a speed time graph. Okay, velocity time graph. Okay, so usually when we want to calculate the area under a graph, we would do, and we have, let's say we have a let's say we have a graph here. Okay, let's just add a graph here. Okay, so, and let's say that this was our velocity. We have a constant velocity of 5 meters per second for 5 seconds. Okay, now if we draw an imaginary line here, so if that's 5 seconds and that's 5 meters per second, well, because speed equals distance over time, and we have the speed, we have the time, we could do speed times time, which is essentially the area here, which is going to be 25 meters. Okay, now it gets a little more complex when we're dealing with a curved area like this. And at GCSE, we may have looked at a method where we instead try and approximate the area. Okay, so at GCSE, we may have used a trapezium rule, and this would have given us an approximate area under the graph. Okay, but one thing that I'd like you to notice is that the smaller the width of the rectangles here that we use, okay, the more accurate, okay, that's a pretty bad rectangle. The more accurate, okay, so the smaller the width of the rectangles here, okay, that's going to give us a more accurate representation of the area under the graph, because you can see that we're missing out quite a big portion of the graph here when we're using the bigger rectangles with the bigger widths. When we're using the rectangles with the smaller widths, there's much less area where we can go wrong. Okay, so one way we can imagine this is that if we have a plane here and it wants to go from A to B, and it moves like this, where it speeds up and then it slows down. It doesn't have a constant acceleration where its velocity is going in a, where we have a straight line on this graph, but it moves from A to B within 6 seconds. So essentially what we just did here was we modeled the plane as having a constant acceleration, because if we think about it, in this rectangle here, we've calculated the exact distance the aircraft has traveled, but we notice that the velocity is in a straight line. It's not in a curved line like here. It's in a straight line, which means that it's moving at a so I think a better way to understand this, okay, is that if we have a box here, then the velocity here is in a straight line. It's not in a curved line. This is 5 meters per second. Okay, this velocity here is constantly changing, but for a period of let's say 2 seconds, the velocity is constant at 5 meters per second. So essentially what we're doing is, instead of modeling it like this, where the velocity is constantly changing, what we're actually doing is doing it like this, where we model the constant acceleration as being a fixed value for a fixed number of time. And we notice that the smaller the time taken for constant acceleration, okay, that's going to give us a more smooth representation, and eventually we're going to get an actual depiction of how the plane is moving. Okay, so now you're probably asking yourself why we have all these strange symbols here, and essentially what I'm trying to say is that we know that if we make these rectangles smaller and smaller and smaller until they approach a value of an infinite small width, like this line here, what we're going to get is something like this. Okay, we're going to get an infinite number of rectangles with an infinitely small width, all which have a height which corresponds to a point of the function of the graph. Okay, because look, if this is a rectangle here, okay, with an infinitely small width, it corresponds to a point on the graph. Okay, so we know what the height is, but it has an infinitely small width. So we have these infinite series of rectangles here. Well, we can see that, okay, maybe if I was better at drawing, we'd see that essentially we've got the complete area of the graph now. Okay, and this is what Riemann sums are trying to say. It's trying to say that as sorry, there should be a limit here as well. It should be limit. So if we add the limit as n tends to infinity, okay, n being the number of rectangles we have here, well, let's go back a bit and see that the more rectangles you add, the smaller the width becomes. Okay, so the width of the rectangles is proportional to the number of rectangles you have. So if you have the infinite number of rectangles here, you can see that as n tends to infinity, okay, the width of the rectangles, aka the change in x, which is the width of the rectangle, that's the change in x, okay, that's going to approach 0. Okay, so as you have this infinite, so almost infinite series of rectangles, their width is essentially going to be 0. Okay, and while we're not going to physically add up the area of all these rectangles, what calculus and integration therefore allows us to do is that we can use these upper and lower bounds 0 and 6. Okay, so we know that the sum of all the widths of these rectangles, okay, is 6. Okay, so we're not, so that's sort of just to help you think a little better, but we know that that the area of these rectangles is bounded by 0 and 6. Okay, so essentially what we're doing is that with integration, we're finding we're obtaining the change. So for every rectangle, okay, it has a different height. Okay, so essentially because their widths are almost 0, essentially 0, we are finding the sum of the change in the graph, okay, in order to find the area, which is integration, okay, where we take all these infinitely thin rectangles, okay, and if we have if we have b and a as our limits 0 and 6, we can find the area here. I hope that was useful, and if you have any outstanding questions, leave them in the comments. Remember, this is one video of many online, so if you want to dive deeper, there are plenty of videos like this out there. I will most likely be making follow-up videos to explain this, but for now, that's the end. I hope you found this useful, and if you haven't already, please subscribe, and thank you for watching. Goodbye.